Hello and welcome. My name is Rad Salman, and I am going to present an extended abstract contribution to this conference called Branch and Bound for the Precedence-Constrained Generalized Traveling Salesman Problem. The work is co-authored with my colleagues Fredrik Ekstedt and Peter Damaschke, and a more complete version has been recently peer-reviewed and published in Operations Research Letters for those who are interested. I am sure that many of you are familiar with the asymmetric traveling salesman problem, where one is required to find a shortest tour in a directed edge-weighted graph. In this variant, the precedence-constrained generalized traveling salesman problem, or PCGTSP, the vertex set is partitioned into several subsets, or so-called groups. We are then required to visit exactly one vertex in each group. Furthermore, there may be precedence constraints, which dictate that some subsets must precede others in the directed tour. These are usually formulated through a separate directed graph, where an edge PQ means that group VP must precede VQ in a feasible tour. The reasons for studying this problem is that it arises naturally for many applications in the manufacturing industry. There are many processes which require an efficient ordering of tasks, which can be performed in several different ways. Moreover, there may be some partial ordering imposed on the sequence of tasks because of purely physical constraints or other process-specific reasons. Our main contribution in this work is a novel branching strategy for the GTSP, together with an adaptation of a specialized pruning technique first proposed by Shubaki and Jamal in 2015 for the non-generalized case of the same problem. So rather than branching on edge variables, which is quite common for TSP variants, we branch on group order. Every tour is required to begin at the starting group, V1, so this is the only group that is fixed at the root node here in the branching tree. Every branch then corresponds to a choice of which group to visit next. So for example, sigma 1 here contains the group sequence V1, V3, while sigma 3 contains the sequence V1, V3, V6. The branching tree node n of sigma represents a PCGTSP subproblem, where the tour is required to begin with the group sequence defined in the sequence sigma. So for example, n of sigma 3 corresponds to a subproblem of the PCGTSP, where any feasible tour must begin with the sequence V1, V3, V6. The optimal choice of vertices can then be decided easily and efficiently by dynamic programming for any fixed group sequence. There are two main reasons for using this branching strategy. Firstly, the number of groups is naturally much smaller than the number of vertices and vertex edges. A group typically contains around 10 vertices, but can contain as many as hundreds of vertex choices. So the size of the branching tree is severely limited by this strategy. Secondly, it turns out that we may divide the set of branching tree nodes into equivalence classes based on the principle of optimality for the TSP. There are on the order of m times 2 to the power of m such equivalence classes or subsets, which together define a partition on the whole set of branching tree nodes. More specifically, we say that two tree nodes are equivalent if and only if their group sequences are such that they traverse the same set of groups and start and end on the same group. For example, if sigma I is V1, V3, V6, V5, and sigma j is V1, V6, V3, and V5, then the corresponding tree nodes n of sigma I and n of sigma j are equivalent. Then it turns out that we can exploit some properties within these equivalence classes. For example, we know that within an equivalence class, the tree node which corresponds to the group sequence with the shortest cost of traversal is the only one that can belong to an optimal branch. So if we store the smallest cost discovered so far for each equivalence class, we may directly prune any tree node we come across within this equivalence class with a higher group sequence cost. Furthermore, it turns out that if you define the subproblems at the tree nodes in a certain way, we must compute the most cumbersome part of the lower bound computations at the tree nodes only once per equivalence class. We tested this algorithm on several synthetic and real-world problem instances with a time limit of 24 hours. We found that the largest problem instance that was solved had 50 groups and hundreds of vertices. The scaling for large numbers of vertices is in general quite manageable. While the pruning method we describe in this presentation is powerful, the different methods for computing lower bounds that we have evaluated are quite weak. This is probably due to the fact that the precedence constraints are almost completely relaxed in this part of the algorithm and are quite difficult to incorporate. Lastly, in industrial use, the situation often calls for several robots or workers to complete a set of tasks together as efficiently as possible. So there is a need to extend this work to the multiple agent case, which is of course more complicated. Thank you for listening.